Hi everyone, this is lecture 4, and in this lecture I'm going to be reviewing some things about light and teaching you some new things. Obviously it's very important for us to study light and to know the characteristics of light, because in astronomy the only way we know anything about objects in space is by the light that they give off. So what I want you to do before I continue is just to pause the video for a minute and try to remember everything you can remember about light from physics, and then I'll go through and remind you of some of the key things. So hopefully you've done that now, and here is a reminder of some of the big ones. First off, we should remember that light is a wave, and it is an electromagnetic wave. That means that the wave is made up of vibrating electric and magnetic fields. It's a transverse wave. That's the kind that have crests and troughs, unlike sound waves, which has compressions and rarefactions. This means that it's able to travel through the vacuum of space, which is pretty important, obviously. It has a wavelength, and the wavelength tells you something about the color. And just like any wave, it can go through the basic processes like reflection off of a mirror, refraction when it goes from one medium into another, interference when there's two waves and they meet up. There's actually some important astronomical techniques based on interference, and diffraction, which is also going to be very important for us in astronomy. That's when you pass light through a small gap in a barrier and it spreads out. Another thing that's going to be really important to us in astronomy is the fact that it undergoes the Doppler effect when the source of the waves is moving. And of course, light travels at the speed of light, which is 3 times 10 to the 8th meters per second. Hopefully we can remember from physics that the wavelength is the distance between two crests. And I've got two waves here. We've got a short wavelength one and a long wavelength one. And the wavelength is related to the frequency of the waves, the number of waves that pass each point per second. So you can clearly see that something with a shorter wavelength, you're going to have more waves pass a particular point per second, so there's a higher frequency. And the relationship you should remember from physics is that the speed of a wave is equal to the wavelength times the frequency. V equals lambda f. Of course, when we're dealing with light waves, the speed we're going to use is going to be the speed of light. We'll use that for V in all of the problems in here. Those are the only kinds of waves we're going to be dealing with. And this formula does imply that when you have a long wavelength, you have a low frequency. When you have a short wavelength, you have a high frequency. Now, in physics, I spent a lot of time trying to persuade you of the fact that light is a wave. And the big clincher experiment that we talked about was the interference experiments. I showed you that light does interfere, and that when you put two waves together, you can get both bright regions on a screen and dark regions. That is definitely something waves do. Particles don't do that. But it turns out that there are other experiments that you can do that are equally convincing that light is a particle. And this is a really confusing concept. There's another experiment, it's called the photoelectric effect. If you're interested, we can talk about that in class. But in the photoelectric effect, light acts like a particle, not like a wave. And this evidence is every bit as strong as the interference evidence is for light being a wave. This is equally convincing. So how do we reconcile this? Well, what Einstein did, and this is actually what Einstein won the Nobel Prize for, was explaining that light is both a particle and a wave. And what you see depends on the experiment that you're doing. So we talk about things called photons. Photons are particles of light, but they sometimes act like a wave. These are supposed to be illustrations of photons. It's really hard to illustrate a photon, but you can see there's a wave, And it's sort of like the little wave is confined to just a small region instead of being something that extends evenly through space. The wave seems to be confined to a small region. So a photon, which we'll talk about a lot here, is a particle of light that sometimes acts like a wave depending on what experiment you do. This is a very weird concept. If it doesn't seem weird to you, you're not thinking about it hard enough. This is almost like me telling you that a baseball is a wave. Well, actually, a baseball is a wave. It turns out that it works both ways. Another weird aspect of this theory. But it's supposed to be strange. It's supposed to be confusing to you. So, but you will just have to sort of take my word for it on this one. Light is both a wave and a particle. And photons have energy associated with them. This is an important formula. This is a new one for you. The energy of a photon is equal to a constant called Planck's constant, for Planck, the scientist who came up with this, times the frequency of the wave. Now we're going to use some really bizarre units for energy. We normally use joules for energy, but it turns out joules are ridiculously huge for the energy of a light wave. So we're going to use a different kind of unit called an electron volt. You don't really need to worry about what that is, just know that it's a teeny tiny fraction of a joule. Very, very small fraction of a joule. And we're going to measure our energies using these units because the numbers work out nicer. H is a number called Planck's constant. This is a constant of nature, and it's got a value of 4.14 times 10 to the minus 15 electron volt seconds. This is a useful number to program into your calculator. I can help you with that if you need some help with that. And F is just going to be our frequency measured in hertz. So I'm going to show you how this works in a simple example, and you're going to try some more when you come to class. But let's go to your packet and look real quick at number 15. What we have in number 15 is an AM radio station, and this is a very typical frequency for an AM radio station, 1,120 kilohertz. Now we're going to need to get things in the right units before we proceed. We can't have kilohertz. We have to convert our kilohertz to hertz. So hopefully we remember that kilo means 1,000. So 1 kilohertz is equal to 1,000 hertz. So I've got 1,120 kilohertz. I'm going to set up a conversion, and kilohertz is going to go on the bottom because I want the kilohertz to cancel. So those go away, and I'm left with 1.12 times 10 to the 6th hertz. That sounds like a big number, but actually that's a very low number for an electromagnetic wave. Then I want to find the wavelength. Well, v equals lambda f. This is a physics problem. Our v is the speed of light, c, 3 times 10 to the 8th. I've got that programmed in my calculator, so I'm not going to bother to write out the number. And when you solve for the wavelength, you end up getting 267 meters. Very, very large wavelength. These radio waves have very long wavelength. And then the energy is equal to Planck's constant times the frequency. Planck's constant will be given to you. You know what that is. And when I multiply that, I get a very small number, 4.6 times 10 to the negative 9 electron volts. This is a very, very small energy. Things with low frequency have very, very small energy. When we get to visible light, we'll see that the energy turns out to be like 2 electron volts or something like that. And I'll stop there. Make sure you ask me any questions if you don't get this in class.